organizers for their kind invitation and for suggesting the subject of this survey talk. It was a welcome opportunity to familiarize myself with recent progress in the subject. So before I prepared the talk, my title was this one, Additively Finite Triangulated Categories of Riedtmann and many other people. Now, while I was preparing the talk, I became aware of the fact that Fernando Muro has really solved well, the problem for a large and important class, and maybe the only class for which we can hope for a solution. So let me slightly change the title. Now it's from Riedtmann to Muro. Okay, let me start by defining the terminology. Let us take a Kroll-Schmidt category. If you don't remember what that was, then you can have a look at the glossary at the end of the handout. It's an additive category where indecomposables have local endomorphism rings and each object decomposes into a finite sum of indecomposables. And that decomposition is then essentially unique. Now, let's take such a Kroll-Schmidt category. We say that it is additively finite if it has only finitely many isomorphism classes of indecomposables. And then it has a well-defined Auslander algebra. Let me recall how this is constructed. We take our additively finite Kroll-Schmidt category. We choose a set of representatives of the indecomposables that are only finitely many. So the sum of these indecomposables is well defined. And then the Auslander algebra is the endomorphism algebra of this sum. Yes, this sum is known as an additive generator of our category. And then we get an equivalence between the Kroll-Schmidt category we started with and the category of finitely generated projective modules, right modules over its Auslander algebra. And the existence of such an equivalence characterizes the Auslander algebra up to Morita equivalence. So all the additively finite Kroll-Schmidt categories are really categories of projective modules of algebras, and we will use this a lot. So now let's become more specific. Let us fix K a field, and from now on, by a category, I will always mean a K-linear homofinite Kroll-Schmidt category. So morphism sets in this category are finite dimensional vector spaces. Okay, and then a distant goal would be to classify the additively finite triangulated categories T in this sense. Now, why is this an interesting problem? It's an interesting problem because there are interesting classes of examples of such categories. The historically first class probably comes from representation theory of finite dimensional algebras. Suppose we have a self-injective algebra, an algebra which is finite dimensional and injective as a module over itself. And let us, well, in that case, the category of finitely generated right modules is a Frobenius category, a category with enough projectives, enough injectives, and where these two classes coincide. And its stable category, obtained by dividing by the ideal of morphisms factoring through a projective, is canonically triangulated by a result of Heller and Happel. And if the algebra we started with is representation finite, if it has only finitely many isomorphism classes of indecomposables, then the same holds, of course, for this stable category. So we get an additively finite triangulated category. And this class of examples, more precisely the corresponding algebras, were completely classified over an arbitrary algebraically closed field by Riedtmann between 79 and 83. Now the second class of examples comes from commutative algebra. Suppose we take a complete local Gorenstein algebra, commutative Gorenstein algebra R over a field of characteristics 0, which is algebraically closed. Then we look at its category of maximal Cohen-Macaulay modules. This is again a Frobenius category, so its stable category is triangulated. And if the algebra has only finitely many indecomposable Cohen-Macaulay modules up to isomorphism, then this is another example of an additively finite triangulated category. In this class, these were classified by Buchweit, Scoil, and Schreier in '87 and by Knever also in '87, and these turn out to be simply the simple singularities. Now, a third class of examples comes from cluster theory. Yes, when Buan, Marsh, Reinicke, Riedtmann, and Todorov invented cluster categories in 2006, they constructed them as orbit categories. In our case, we take the orbit category of the derived category of a Dynkin quiver of type ADE, say, by the automorphism, by the group generated by some auto equivalence, such that the quotient is additively finite. Then we get this class of orbit categories. This class actually contains the class of the second example. And well, if we also admit deformations, suitable deformations of categories, then we also get this class as a subclass of this number. So this is, if we take this class and admit deformations, then we get both classes. Okay, and now, apart from these examples, we have a general theory, and this has recently witnessed progress by Fernando, as I already mentioned. He proved Auslander correspondence for the algebraic K-linear additively finite categories over an arbitrary perfect field K. So he described exactly the image under the Auslander, under the functor taking a category to its Auslander algebra. He described the image of the class of algebraic K-linear additively finite triangulated categories. So I will come back to this later. So for the moment, the plan is as follows. I will start by recalling which Auslander-Riedtmann quivers can occur for additively finite triangulated categories. Then I will examine the possible K-linear structures. The existence of a triangulated structure imposes severe restrictions on the possible K-linear structure, and I will describe these. And then I will turn to the case of an algebraic additively finite triangulated category and describe Fernando Muro's results. Okay, and so let's start with the Auslander-Riedtmann quivers. Let's work over an algebraically closed field for simplicity. And let's take T, a connected and additively finite triangulated category over this field. Then Xiao and Zhu in 2005 describe the Auslander-Riedtmann quivers. Well, first of all, of course, one has to show that there are Auslander-Riedtmann triangles, or equivalently, the category T has a cell functor. And then, so then the Auslander-Riedtmann quiver is well defined, and we can describe it as an orbit quiver, where delta is an ADE Dynkin diagram, which is unique. And G is a group of automorphisms, a weakly admissible group of automorphisms. If you don't remember what weakly admissible was, you can have a look at the glossary at the end, but it does not play such an important role for the moment. So we get certain orbit quivers, and we may ask whether all of them appear, and that is actually the case. Yes, this, yeah, maybe, well, before that, one word on the proof. The proof is based on Wienberg's characterization of Dynkin diagrams via sub-additive functions adapted to representation theory by Happel, Preiser, and Ringel in 1980. And now, yes, there's a question which orbit quivers appear. And well, they appear all of them appear. This is an observation by Amiot in 2007, namely, if we want to construct an additively finite triangulated category with a given orbit quiver, well, all we have to take is the orbit category of the bounded derived category under an auto-equivalence, which lifts a generator of our weakly admissible group. Yes, Riedtmann has classified all these weakly admissible automorphism groups. They all turn out to be cyclic, so we can just take such an orbit category under a unique auto-equivalence. Okay, so let's look at some examples. Yes, as already mentioned, these these orbit categories are generalizations of cluster categories invented by the 5 authors in 2006. So recall the cluster category is the category which we get by dividing the bounded derived category of our Dynkin quiver by this auto-equivalence. This is precisely the auto-equivalence which we need to make the orbit category 2 Calabi-Yau. Here S is the cell functor, sigma is the suspension. If we want the suspension to become the square of the cell, sorry, if we want the cell functor to become the square of the suspension functor, then this is the auto-equivalence which we need to factor out. And then we have the corresponding Auslander-rating quivers, which you may have seen before. Yes, here we have in type A, this auto-equivalence, this magical 2 Calabi-Yau auto-equivalence by reflection, the infinite strip. So the quotient is this Möbius band. In type Dn with odd n, the auto-equivalence is just a translation. So the quotient is such a cylinder. In type E6, again, we have a glide reflection as auto-equivalence, and we get this nice Möbius strip. And in all these examples, the automorphism group is actually admissible, and there are no loops in the orbit quiver, but we also have examples where there are loops. Yes, so this is the case where G is only weakly admissible. So we take an A4 quiver, we take its repetition quiver, and we divide by the auto-equivalence, which maps this piece to this piece. So again, you can see it's a glide reflection. You can see that all these vertices lie in the same orbit, represented here by this vertex. And then you see that these arrows all give rise to the loop in the orbit quiver. So we get such loops, and this is essentially the only possibility of getting loops. Yes, so you get bigger examples by taking bigger AN quivers, but that's essentially the only possibility. So this gives a family called LN. Okay, so much for the Auslander-rating quivers. They are perfectly well understood. Now let's come to the K-linear structure. And to describe the restrictions imposed by the existence of the triangulated structure on the K-linear structure, we need to recall some very classical results going back to the 60s in work of Fried and Keller. Here we can work over an arbitrary commutative ring, and we take T, a small Puppe triangulated category. Well, a Puppe triangulated category is just a triangulated category which does not necessarily satisfy the octahedral axioms. Yes, so these were invented in the 60s by Puppe, independently of Grothendieck-Verdier. And so they give much of the basic theory of triangulated categories also works for Puppe triangulated categories, in particular the long exact sequences in Hom induced by triangles. Okay, so let's take this category. Then we can look at homological functors from T to abelian categories, and there is one universal functor, which is the uniter functor with values in this category of finitely presented functors. Yes, mod T is the category of finitely presented functors from T to mod K. What is a finitely presented functor? Well, it's simply the co-kernel of a morphism between representable functors. X hat is the representable functor associated with X. And well, first observation, this is an abelian category. Yes, this comes from the fact that the category T has weak co-kernels. Any triangulated category has weak kernels and also weak co-kernels, but what we need here is weak kernels. And so this ensures immediately that we have an abelian category. And then what is less immediate, it is also a Frobenius category itself. Yes, this was shown by Fried. It has enough injectives and enough projectives, which are just the representables, and projectives and injectives coincide. Okay, and now a result by Heller, namely using the triangulated structure, the Popper triangulated structure, we can construct an isomorphism of triangle functors as follows. Yes, so we look at the stable category of this Frobenius category. And in this stable category, we have the suspension functor associated with it. And then Heller's theorem says that the third power of this suspension functor of the stable category is isomorphic to the functor of the suspension of T. As T is a triangulated category, it has itself a suspension. This suspension induces an autoequivalence in the module category, and this induced autoequivalence is isomorphic to the third power of the suspension in the stable category. So notice that this only depends on the additive or the K-linear structure of the module category, and so only on the K-linear structure of the triangulated category. This functor depends on the choice of suspension, and this isomorphism depends also on the triangulation. And in fact, Heller proved that the map taking a triangulated structure to this isomorphism is a bijection when we fix the suspension functor. But we won't need this, we only need the existence of this isomorphism when there is a triangulation. And where does it come from? Well, it's very straightforward. Yes, suppose, well, let's construct this isomorphism. Yes, suppose we have a finitely presented functor. Yes, then by definition, it's the co-kernel of a morphism between representable functors. Okay, so that comes, of course, from a morphism between X and Y, and we can form the cone over this morphism. So we get a triangle, and this triangle gives us a long exact sequence in the Hom functors for any Popper triangulated category. Okay, now let's look at this sequence more closely. Yes, so here we have the functor f, and then here, as you can see, we have the image of the functor f under the autoequivalence induced by sigma. Yes, so this appears here naturally as a co-kernel. Yes, so this is this applied to f, which we have here. Here we have f itself, and between these two, as you can see, we have an exact sequence. And the three terms of this exact sequence are injective. Yes, because they're representable and we are in a Frobenius category. And that means, well, if we have, here we have an exact sequence, three middle terms injective, and then the co-kernel, well, that's the definition of the third power of the suspension. So we see that this object is naturally isomorphic to the image under the third power of suspension of this object. And so that's the construction of this isomorphism, and its existence is the crucial restriction which is imposed. Okay, now let's take a perfect field. Let's take a finite dimensional connected basic and non-semi-simple algebra. And well, so its category of projective modules is a candidate for an additively finite triangulated category. So suppose it is such a category, suppose it is Puppe triangulated, then if we look at Heller's result, it tells us in particular that the third power of the suspension functor of the module category over A permutes the simple modules. Yes, the module category over A is, in this case, the category of finitely presented functors. This third power is simply induced by the suspension functor of A, which is an autoequivalence of Prosh A, and this autoequivalence of Prosh A, of course, permutes the simple modules. Okay. Now, in this situation, by a result of Green, Sneshel, and Solberg, slightly generalized by Hanihara, we find that the bimodule third suspension of A as a bimodule is invertible. Yes, it's invertible as a bimodule. There's another bimodule such that the tensor products on both sides are isomorphic to A as a bimodule. Yes, so this is then by definition what a twisted periodic algebra is. So we find this restriction on the K-linear structure. Yes, the K-linear structure is encoded in A, and A is quite special. It is twisted 3-periodic. Okay, and of course we may ask whether this necessary condition for the existence of a triangulated structure is also sufficient. Yes, so can we go the other way? And surprisingly we can. And we actually don't just get a Puppe triangulated structure, we get a real, true, honest to goodness triangulated structure with the octahedral axiom. Okay, so this is a theorem by Keller and Muro. So let me introduce some notation. Let's take T, the third suspension of A as a bimodule. Then by definition of the third suspension, we have an exact sequence with three injective middle terms, and we can choose it minimal with no contractible summons. And this will yield the triangles. Yes. So Claire and Muro showed that the category of projective modules over A has a triangulated structure with the octahedral axiom, whose suspension functor is given by tensoring with this invertible bimodule. And the triangles are simply of this shape. Yes, I abbreviate the tensor product by this functorial notation. Yes, we just take any finitely generated module over A, and we apply the functors associated with these bimodules. That's these are the standard triangles, and by definition, any other triangle is isomorphic to a standard triangle. Okay. Yes. So one subtle point is that when we go in this way around the cycle, then we have no reason to expect that we get back to the same triangulated or Puppe triangulated structure. Yes. So we just have an equivalence of existence. The existence of such a structure is equivalent to this property, but we have no control on the structure itself. In particular, it might change when we go around. Yes. But anyway, so as a corollary, as observed by Hanihara, we have this equivalence. Prosh A admits a Puppe triangulated structure if and only if A is twisted 3-periodic, if and only if Prosh A admits a triangulated structure. Okay, and so as I said, so this characterizes the possible K-linear structures, but it does not characterize or classify in any way the possible proper or strictly triangular structures. Okay, yes, so we will use this characterization in a moment. Let me just point out one other consequence of Claire's theorem, namely, it allows us to construct many more examples of additively finite triangulated categories, and in particular, so-called non-standard examples. Non-standard in the sense that the category cannot be presented by its Ausländer-Reitenkurve with the mesh relations. Yes, the category is called standard if it is presented by the Ausländer-Reitenkurve with the mesh relations. And here we get examples which cannot be presented in that way. Yes, let me just look at one example. Yes, all the known examples live in characteristic 2. So let's take a field of characteristic 2, and let's take this pre-projective algebra of the Dynkin quiver of type, of a Dynkin quiver of type D4. Yes, so here this is actually an Ausländer-Reitenkurve. Yes, the Ausländer-Reiten translation is the identity, and the mesh relations are simply the pre-projective relations. So this is just the pre-projective algebra. Now, if we took this, then of course it would be standard. But it turns out we can perturb these relations and conserve the twisted three-periodic property. Yes, and they are perturbed in this way. Yes, we add this red term to this relation, and we add this relation of order 4. Yes, and so surprisingly, it remains twisted three-periodic, so it still defines a triangulated structure via Claire's construction. And it is not standard, yes, by construction. Well, of course, you have to check that indeed these deformed relations are not equivalent with the mesh relations, but okay, that can be done. Okay. And now let me come to the algebraic case. Okay, let me first recall what an algebraic triangulated category is. Well, it's a triangulated category which is triangle equivalent to the stable category of some Frobenius exact category. And we have known since '94 that this can also be described by saying that it is equivalent to the perfect derived category of some small DG category A, where the perfect derived category is the full subcategory of the whole derived category formed by the compact objects, those whose associated covariant Hom functor commutes with arbitrary co-products. Yeah, so yes, if this was an algebra, this would be the homotopy category of bounded complexes of finitely generated projective modules. Okay, so this defines what an algebraic triangulated category is. And in this case, with these notations, the DG category A is then called a DG enhancement of our triangulated category. And we also have a notion of equivalence for the DG enhancements, namely, it's simply Morita equivalence, derived Morita equivalence. Two enhancements A and B are equivalent if we can find a bimodule whose derived tensor product induces an equivalence between the two perfect derived categories. Okay. Now it would be natural to require this equivalence to be compatible with these equivalences. Yes, so it would be natural to require this triangle to be commutative once we fix these equivalences, but we do not require that. Yes, we don't require that because we have no idea of how to prove it in practice. Yes, so that's because of our ignorance, we do not require this natural condition. So, yeah. Yeah. Okay, and now let me state Muro's theorem. we work over a perfect field. So, and we take an algebra, which is twisted 3-periodic. Okay, so its category of projective modules carries a triangulated structure. And the first part of the theorem tells us that this triangulated structure, this canonical structure constructed by Claire, is algebraic. And that is actually very surprising. Yes, if you look at the construction of this structure, there is no Frobenius category inside, which might yield it. Yes, this is not a model category. Yes, so it's not clear at all why it should be the stable, why should this be the stable category of some Frobenius category? That's not at all clear. And there's also no DG category inside. Yes, and actually many people, including Michel Vandenberg and myself, doubted whether these examples were algebraic at all, in particular the non-standard examples which you can construct. But okay, so Muro proves that it is algebraic, and he proves this by proving that all the obstructions to being algebraic vanish. Yes, I will come back to this proof later. And then the second part is also very surprising. It says that all DG enhancements which we have for this algebraic triangulated structure are equivalent. Yes, so that is also surprising for several reasons. So first of all, we know that definitely it is wrong if we don't work over a field. As here we have worked over a field, a perfect field, and it's definitely wrong if we work instead over Z, for example. And here is a famous counterexample due to Marco Schlichting. We take this additively finite triangulated category, yes, the category of finite dimensional vector spaces over the field with P elements, with the suspension functor given by the identity. There's a unique triangulated structure where all the triangles split automatically. And this can be described in two ways, in at least two ways, as a stable category. We can view it as the stable category of the ring Z modulo P squared Z, or we can view it as the stable category of the P truncated polynomial algebra over the field with P elements. Yes, so these look quite different, and they are actually different. So one can show that they are non-equivalent. They give rise to non-equivalent DG enhancements. Yes, if the DG enhancements were equivalent, then their case theory would have to be the same. But Schlichting, has computed, using calculations of other people, that their fourth higher K theory group is not the same, and so they are definitely not equivalent. And so this appearance of this type of torsion phenomena prevents an analogous statement in this case. Okay, and another reason why it's surprising, that there are some uniqueness theorems known for DG enhancements for derived categories. Yes, so the first theorem of this type is due to Lunz and Orloff. They showed that if we take a quasi-projective variety over a field, then the bounded derived category of coherent sheaves on this variety has a unique DG enhancement. And this has been generalized, yes, to derived categories, now unbounded derived categories of Grothendieck abelian categories. Here the result is due to Caminacco and Stellari from 2018. And it has been further generalized by Antio. Antio considers non-DG enhancement. He considers presentable infinity category theoretical enhancements. So these are definitely more general than DG enhancement, and they are also unique. But all these proofs rely on the existence of a T structure, and in an additively finite triangulated category, there is no non-trivial T structure, simply because the suspension functor is periodic on objects. It's because there are only finitely, it's periodic on indecomposable objects because there are only finitely many indecomposable objects by definition. So So we are in the absence of this crucial tool, and despite the absence of this crucial tool, Muro succeeds in proving uniqueness. Okay. So let me formulate as a corollary to his theorem the Auslander correspondence for additively finite algebraic triangulated categories. Yes, so the category is algebraic. Yes, so we have a bijection between, well, we have to take connected, additively finite algebraic triangulated categories up to triangle equivalence, and a certain class of algebras up to Morita equivalence, namely the connected twisted three-periodic algebras up to Morita equivalence. So from left to right, it's just given by the functor which takes a triangulated category to its Auslander algebra. And from right to left, well, we take the category of projective modules with the Amio triangulated structure. We now know it is algebraic, and we get all algebraic triangulated structures in this way up to. Okay, so now this classification problem here is reduced to the corresponding classification problem for connected twisted three-periodic algebras. So can we solve that? Well, it's a very difficult problem, of course, but it now seems to be solved, yes, at least over an algebraically closed field. This problem seems to be solved. The solution is given in theorem 9.4 in a recent survey paper by Karin Riedtmann and Andrzej Skowronski, which is entitled simply Periodic Algebras. Karin kindly sent me a preprint. It's not on the archive for the moment. Well, she also advised me to point out this paper by Stefania Andreu Juan and Manolo Saurin, where they prove twisted three-periodicity for a certain important class of algebras. Now, this classification is still not entirely stable. Yes, Karin told me it was modulo small corrections in the relations of the deformed algebras. So yes, you remember this subtle example where we deform the pre-projective relations. Yes, so this is really hard computational work, but the essential work seems to be done by all the people who have worked on periodic algebra. So there are a lot of them. I'm not able to cite them all. Okay. So the crucial theorem is, of course, this theorem by Muro. The fact that it is that the Amio triangulated structure is algebraic and that we have uniqueness. So how does the proof work? Let me say a few words on the proof. Yes, it's a proof of about 30 pages. It uses Hochschild cohomology, A-infinity structures, the Tabuada model structure on the category of DT categories, and in a crucial spot, spectral sequences. Okay, so I won't enter into the details. Let me just outline maybe the main steps. Let's start from a twisted three-periodic algebra A. Then we look at the third syzygy of the bimodel A. Let's call it I. So this is the bimodel which is inverse to the bimodel given by the third suspension, of course. And then if we look at the third extension group between the bimodel A and this third syzygy, well then, of course, it's isomorphic canonically to the stable endomorphism algebra of A as a bimodel, and we can look at the image of the identity. So that gives us a certain element, M3 bar, in this third extension group. And now we will interpret this element as an element of a suitable Hochschild cohomology group. Yes, mainly we consider Z-graded algebra B. If you like, it's a Z-graded version of the tensor algebra of this bimodule I. And then Fernando shows that this class M3 bar lifts to a unique class in the bi-graded Hochschild homology in degree 3-1 of this graded algebra B. And this class is unique in characteristic 2. You additionally need to impose this condition: the Gerstenhaber square of this lift should vanish. In characteristic different from 2, you can just say that there is a unique lift. Okay, so we have this class, we have this Hochschild cohomology class, and we can of course represent it by a co-cycle. Yes, I should have written co-cycle. So, of course, every co-cycle is a co-chain, but it's important that it's a co-cycle. M3, well, this M3 is just a linear map from B tensor B to B, and it's homogeneous of degree -1, which represents M3 tilde. And now the point is that this M3 can be completed to an A infinity structure, a minimal A infinity structure on the graded algebra. So this is the crucial theorem, line 1. M3 can be extended to a homogeneous minimal A infinity structure. So minimal means that M1 vanishes. M2 is the given multiplication of B. Then we have our chosen class M3, and then there are some higher multiplications which are non-explicit and which are shown to exist by showing that all obstructions to their existence vanish. Okay, and then one examines to which extent this construction is unique, and one shows that it is unique up to non-unique A infinity isomorphism by showing that the space of possible choices is contractible. Okay, and then at the end, well, we have this A infinity algebra B with the higher structure. Any A infinity algebra is quasi-isomorphic to a DG algebra. I infinity quasi-isomorphic to some DG algebra, let's call it C. And then you show that this, the perfect derived category of this DG algebra is equivalent to the category of projective modules or the algebra we started with. And under this equivalence, the canonical triangulated structure on the perfect derived category corresponds to the Muro triangulated structure on the category of projective modules. Okay, so the crucial point is this theorem 1, line 1, yes. Okay, and how do you prove theorem 9.1? Well, you prove it using spectral sequences. The technical heart is a spectral sequence argument. Yes, it looks like this. You have to chase elements through these spectral sequences. Okay, I have to admit I did not check the details, and well, I'm not. How should I say? I have nothing against spectral sequences, but when I have a choice, I do prefer conceptual arguments. And well, now thanks to Fernando's theorem, we know that there is a triangulated structure and that there is an algebraic structure and it's even unique, yes? So since it is unique, we might hope that we can find a conceptual construction of it. So maybe as a challenge, let me propose to find a conceptual proof showing at least that the Muro triangulated structure is algebraic. Yes, of course, it would be very nice to have also a proof of the uniqueness part, but maybe that's too ambitious. Let's start by trying to find some conceptual proof of the existence of the algebraic structure, there should be some construction. Yes, maybe. Maybe it's not so hard. It's hard to tell. Okay. Yes, so this is essentially the end of the talk. So at the beginning, I showed you pictures of the persons who are at the beginning and the end of this development, Christine Riedtmann and Fernando Muro. Of course, there are many people who have worked on the subject between these two heroes. Yes. So here we have, let me show you pictures of some other people who have worked on this subject and whom I have cited in this talk. Yes, we have at the beginning in the 60s, the foundational work of Fried and Keller, who show that the category of finitely presented functors is Frobenius, and that we have this remarkable isomorphism between the third power of the suspension functor in the stable module category and the functor induced by the suspension of the triangulated category. Then the work of Riedtmann, of course, crucially builds on Auslander-Rayton theory developed by Auslander and Rayton between 73 and 79. The commutative algebra version or commutative algebra analog of Riedtmann's result, the classification for Cohen-Macaulay modules due to Buchwald's, Coyle and Schreier. Then for further progress in the field, of course, the work of Dieter Happel is absolutely fundamental on Auslander-Rayton theory for triangulated categories. Then we have seen the work of Xiao and Zhu, who determined the Auslander-Rayton quiver for actually not only additively finite, but locally finite triangulated categories. Then there was the orbit category construction pioneered in the definition of the cluster category by these 5 authors. Okay, then in 2007 we have Claire's work on the triangulated structure. Henning strengthened the foundations and determined the Auslander-Rayton quivers in the non-algebraically closed case. Then Hanihara put everything known into the nice framework of Auslander correspondence. And finally, Fernando wrote the final thing. Thank you very much.
Thanks, Bernard. So at this point, we reached the question period, and I would suggest to proceed in the following way. So you can simply write your names on the chat list, and I will go through the list of the people wanting to ask questions. And well, you simply turn on your microphones when your turn comes. Would that be okay? So are there questions or comments? Yes, Geoffrey Jensen. So ask your question and turn on your microphone.
So I was actually simply wondering, so Riedtmann classified the stable module category of this representation finite self-injective algebras, but in what terms of what did she classify it?
She classified the algebras themselves, yes?
So really all the algebras itself?
Yes. So there was a second step. So she determined the structure first of the stable module category and then the structure of the module category itself, and from that she got the algebra. So she had the Auslander-Rayton quiver, and she had to determine where to insert the projectives into the Auslander-Rayton quiver.
Okay.
So that's a second step, which is which is not reflected in this talk.
Thank you.
Okay, so if this is okay with Geoffrey, then we have a comment from Shiping. So go ahead, Shiping.
So, okay, I just want to mention that the result on this thinking quiver actually is generalized to arbitrary ring, not necessarily field. And so there result will not be a thinking quiver, but a value thinking quiver. Okay.
Yes.
I
think I mentioned that was Henning's work, no?
I'm not sure.
I briefly,
is my I just copy my result. Okay.
Oh, he just copied your result. Oh, I'm sorry.
Okay, I just.
Oh yeah.
I'm not sure.
Yeah.
I'm not sure how to get the picture. Okay, so anyway, my setting is this just a Schmidt R category for actually. I don't know. Heine has a result. I'm not sure.
Yeah, I have to look
result is very general. That means very Schmidt with this absolute ring.
Yes.
The component is finite, then this finite component should be a thinking quiver modular group.
Okay. I'm sorry.
I can post the result on Skype. I'm not sure I can do it here.
Yeah. Perhaps, Sping, may I suggest that you can handle this very narrow discussion, this very precise topic in a more small group discussion with Bernhard afterwards.
Yeah. That's
and also, of course, if you well, we can discuss about posting something. You can simply contact Thomas or myself, and we will handle it. Would that be okay for you?
Oh yeah, sure, no problem.
Okay.
Yes. So anyway, I have to apologize. I was under the impression that was due to Henning, but it turns out that
I'm not sure. I'm not sure that's due to Henning.
Yeah. Okay. So if shipping is okay for this for the time being, we have a question from Mikhail Gorsky. So go ahead, please.
Hi. You mentioned schlichting counterexample when one doesn't work over a field, instead works over a ring. Over that, yes. So where the argument of Muro fails when one works over that?
Oh, everywhere.
Everywhere. Okay.
Yes. we need a perfect field. I mean, we need to work with bimodels. Yes, we need to take tensor products over our field. We need to know that the tensor product over our field is exact. Yes. So
okay.
So it is just hopeless. Yes.
I see. Thanks.
Thanks. So I have a question first from Claude Sibils and then from Claire. Claude, go ahead.
Yes. I'm curious to know in what sense you are saying that spectral sequence arguments are not conceptual.
Well, I don't know. This is just my personal bias, maybe. I don't know. Well, if I tend to view spectral sequences as a computational tool. Yes, you have lots of indices, you have lots of maps going in all directions. You don't really see what's going on. I mean, I personally don't see what's going on, but maybe other people have better abilities for that. Yes, I have no scientific argument why spectral sequences are not conceptual. Yes, I mean the general theory of spectral sequences. Yes, I think it's a very nice and conceptual theory, but if you then apply it to concrete situations, then I tend to lose the conceptual background.
Okay, thank you.
So can I ask a question?
Yes, who is speaking, please?
Sorry. Sorry, Can you put your name on the list and then we would follow?
My name is Jie Xiao.
But put it on the chat list. Okay, because now Claire was asking to have a question.
No, sorry, I don't know how to manage that, but I just use this ask question. That's okay?
Okay, if that's okay with Claire, I guess we can do it.
Okay. I think Bernhard permitted me to ask a question.
Yeah,
As an
sure.
example, compare with the cluster category, I think for Duncan case, the root category is also very good example.
Absolutely.
Do you
Yes.
think so?
Yes. Absolutely.
So
yes.
maybe you should list that the root category.
I agree.
This is from cover. Okay, right.
Pardon? Yes. Yes.
From
yes.
Harvard.
Yeah, it is of course also a very natural category. Yes,
yes. Also triangular category.
Yes, you divide by the square of the suspension functor. So yes, so you get a very beautiful bijection between all roots and all indecomposables in this triangle.
Right. Yes.
Yes, it's a wonderful example. Yes. Thank you.
Thank you.
Okay, so I think that we can go back to Claire now.
Yeah, so I was wondering whether maybe it could be generalized to the case of n-angulated categories and with n periodic bimodal periodic algebras. Do you think?
Yes, that looks promising. It's yes. I mean the theory of algebraic n-angulated categories is perhaps not yet as well developed as we would need it to be, but I think it's a very interesting question. Yes. I mean, the analog of Heller's isomorphism is definitely true for n-angulated categories. Yes, so we have this. We do get this n-periodic description. So but going the other way, and there's also an obvious generalization of going the other way, which I think works, if I remember correctly. Yes, I think that was also in the paper with Christoph and Stefan. Yes, I think one should definitely explore this.
But is there a notion of DG enhancement for
that's the problem. Yes. So for the moment, there is no proper notion of. Well, I think there is going to be very soon a notion of infinity categorical enhancement. I don't know. We will see.
Okay.
So I'm not aware of a good DG enhancement for the moment. Of course, when the category is realized as a subcategory of some triangulated category, then so at least in that case we could work.
Okay.
I see that there is a comment of shipping pertaining Claire's comment. So perhaps shipping you can do it right now.
Okay. No. Okay, it's okay now. I just want to I want to talk to Claire. Is exactly my result is not only for there's no structure at all. It's for any Kuhl-Schmidt category, additive category. You don't need any structure. Don't need any structure. Just any Kuhl-Schmidt category, which is has only found many object, then the result on this given by this thinking quiver modulo this G is holds. You don't need any other structure for n triangular category. Any Kuhl-Schmidt additive category without any extra structure, that statement is true. That's what I want to say.
Sorry, which statement?
I mean this description of this oscillator component. A valid thinking quiver modular group. And without any, I'm not, actually, I'm not sure about the Keller's, she's talking about which result. I just want to mention that my result is very general. It's an encouragement added category. You don't need any extra structure. I mean, of course, if there's an oscillator sequence, you can define oscillator sequence in any encouragement additive category. If it has oscillator sequence, if the component is finite, then the component is a data is a value equivalent quotient group. Yeah, I'm talking about this. Okay, thank you.
Okay, I have one more comment from Kabe, and then I saw that Pierre-Guy at some point raised his hand. So perhaps we can after these two questions or comments, move to the other platform. I will ask Thomas to share the link again. Okay, so Kaveh, what is your question?
Thank you. Thanks, Bernhard, for the nice talk. I'm not sure how much you can share about the recent result of Karen Erdmanns and Skodronsky, but you at some point alluded to their classification of three periodic algebras over algebraically closed fields, which has contributed a lot to this direction. I'm inclined to think that this classification must relate to their study of the generalized dihedral algebras. Is it, as I mentioned, I'm not sure how much you can share about their work, which is not available yet, but are these three periodic algebras over algebraically closed fields exactly the generalized dihedral algebras, which are...
Sorry, the generalized?
The generalized dihedral algebras, they have been studied under the notion of like weighted surface algebra triangulations?
I'm not sure. Well, I haven't looked at this in detail, but I think it should be more than just the generalized dihedral. That's it. Maybe the hard part is that part, but I think there are more classes which enter the picture.
Thank you.
Okay, thanks. So I saw that Pierre-Guy's hand is not raised anymore.
It was a clapping hand, not a raised hand.
Ah, sorry. Oh. Okay, then I think that we can thank Bernhard again. And well, you see that there is this link that Thomas shared with us. So we invite you to join us in there. You will see it's pretty easy to use. Thanks, Bernhard, again.
Thank you.
So thank you. Can you hear me? Thank you everybody for being here, and I appreciate this opportunity to meet with everybody. And this Zoom is very well organized for having a presentation like this, and it might be less optimal to organize an informal gathering because we need some meeting rooms and breakout rooms. And my son was at a computer science conference, and there they use a different tool called gather.com. And I would, so the formal part of the meeting is over. Thank you very much. And I would like to invite you, if you want to talk, to meet us on this gather.com, gather.town. You see the link. And I'm trying to show you something, but I don't find it at this moment. No. So anyway, you see the link in the chat, and if you click on the link, you don't need to do anything. You just go there, and it has the feeling of a computer game, of a video game. Yeah. So you're a little character, and please give your character some name that we can recognize. So I will call myself Thomas. And then it has the setting of a conference room, of a large building. And the thing is organized by interaction distance. So when you see some people, you want to talk to them, you just go close to them. And when you are close enough, then their video will pop up and you can communicate, you can talk to them. Yeah. And if you go further away, then this disappears, you cannot talk to those people. So you can hide in your corner if you wish. And or you can meet with anyone you like to do, and there's there's some labels, so you can change the interaction distance. There's some concentric circles, and you can chat, you can locate people if you don't find anyone, and you can also go all the way down south to the beach if you just want to hang out a little bit. Okay, so if you like, you can try this and join me there. Kavi has a question about this gathering. Yes, Kavi.
Yeah, you said you want to call yourself Thomas. Don't you mind if I call my character Thomas's friend?
No, you should treat this. You should treat this like your name tag in a real conference.
Oh, gotcha. Okay, yeah. So it's not that much of joy of the computer game freedom.
No, don't call yourself Spider-Man or something. This is a conference, and this is your name tag, and we can recognize you there like this.
Too formal for a gathering. Okay, thank you.
Okay, so thank you very much all for coming.
There's another problem, Thomas.
Yes, there's a problem.
I think it works only for Chrome and Firefox.
It works only for Chrome and Firefox, yes.
So Safari users are out of the game.
Out of the game. You need Chrome.